Okay, today we are introducing the concept of the least squares regression line, but we're first going to start off by revisiting the concept of the sum of squared residuals. So if you can remember from the topic 1 notes from yesterday, when statisticians compare modules to see which one makes the best prediction, they compare what's called the sum of squared residuals, which we talked about at the very end of the topic 1 notes. And remember, they always want to pick the model that gives us the smallest sum, because the smallest sum means the actual values are closest to the predicted values, which is what we want. So maybe we want to highlight this, sum of squared residuals, and we want the one with the smallest sum. This is called the least squares method because that means they're minimizing that distance from the prediction to the actual value. And I'll show you why we use least squares, because our predicted point is located actually on our least squares regression line. So the scatter plot over off to the right here shows the sum of squared residual using that predicted winning percentage formula from the previous day's notes with different exponents. Remember I told you in the second example in the topic 1 notes, technically we could use x for the exponent and we could try all different exponents and see which one gives us the smallest sum. So notice the x-axis here displays the exponent that was used, and the y-axis displays your sum of squared residuals, which we'll just abbreviate with SSR. We should look at the lowest point on the curve, because the lowest point on the curve will give us the one with the smallest sum. Since our y values are the sum of squared residuals, it gives us the smallest sum. So if you look closely, we're going to look at the lowest point on the curve, indicating the lowest SSR, to determine the best exponent. So notice the lowest point on the curve, which gives us the best exponent. So since exponent is our x variable, it's right around 2. Okay, that lowest point occurs, one of those two, okay? So right around an exponent of 2. So that would be the best exponent to use here, because again, it gives us the smallest sum of squared residuals. So we're going to use data from the 2008 Major League Baseball season to investigate the relationship between various statistics, okay? And here we're going to look at the relationship between home runs and runs scored for each team. So here's a scatter plot showing the relationship between number of home runs a team hit and their run totals for each team. The correlation, so this is going back to chapter 10, the previous chapter. The correlation here is 0.62. Describe the association. Or if you can remember specifically, let's interpret the correlation value. So there is your first, one thing we gotta talk about is strength, weak, moderate, or strong. So this should be moderate. Since the values between 0.5 and 0.8, there's a moderate. The sign here is positive, so there's a moderate, positive. Remember, R describes the linear relationship between two variables, so moderate, positive, linear relationship. Between home runs and runs scored for 2008 Major League Baseball team. Or you could write home runs and total runs, whichever. But this information is specifically for 2008 Major League Baseball teams. So that's just a little recap there from chapter 10. Okay. Now it says, when a relationship between two numerical variables is linear, we can model the relationship with a least squares regression line. Some of you guys in the past may have heard the term best fit line in algebra. It's pretty much the same thing. This line is the line with the smallest sum of squared residuals, meaning it's as close to all of the points as possible. So here it is, least squares regression line. We can abbreviate it LSRL. And it can be one in either of these two forms, okay? Now, think back from algebra, the coefficient attached to the x, there's two parts of the line, right? Coefficient of x is your slope, and your constant is the y-intercept. Since this one is one you're more familiar with from algebra, I'm going to focus more on that one. But it doesn't matter, it's same thing. The hat above the y. So notice there's like a little symbol above the y. We call that hat. It's read as y hat, and it indicates that this value is a prediction and not the actual value. You guys, all the points on the least squares regression line are predictions. It's what we predict to happen for a given x value. Doesn't mean it's what's actually going to happen. So we're going to use the scatter plot above that shows the relationship between home runs and runs scored for 2008 Major League Baseball teams. It says the equation of the least squares regression line is this: y hat equals 1.25x plus 550. Okay, where x is what? Well, x is my home runs. And y, let's put a little hat over that. Y hat is predicted runs. Remember, the little hat means predicted. Okay, so it's the number of runs that are predicted to happen based on this least squares regression line. And that line is based on the prediction using all these actual values. So the line, if I were to draw it in, it says a line that's as close to as many of the points, all the points as possible, I should say. So if I were to sketch it, look something like this. And here's the equation right here. So here we go. Once we calculate the least squares regression line, we can use it to make predictions. So it says in 2008, the Texas Rangers hit 194 home runs. Use our least squares regression line, so this equation right here, to predict the number of runs scored by the Rangers in 2008. Perfect. I know that they hit 194 home runs. And remember, x is the number of home runs hit. So I'm going to take the 194 and plug it in for x. So y hat equals 1.25 times 194 plus 550. You can type that all in at once. And you get 792.5 runs. Please make sure to show your work. Please make sure to label your answer. You could leave it like that, or you could round it to 793. Either one is fine. It's a prediction. Okay, so remember, it's not surprising that sometimes our predictions have decimals, but if you'd rather show your work and then write about 793 runs, that's fine. Now, the Rangers actually scored 901 runs. Calculate and interpret the residual. Okay, so remember from the previous day's notes on topic 1, residual, the formula for residual is actual minus predicted. What actually happened? The Rangers scored 901 runs. What did we predict to happen? Well, we plugged in the 194 into our least squares regression line to make a prediction, and we predicted that they would score 792.5 runs. So the residual was 108.5. Or, again, if you want to round that to 109, that's fine. Just show your work. So, interpret the residual. Our residual is positive, so the Rangers, the 2008 Rangers, scored 108.5 more runs than predicted. Based on what? What was our prediction based on? This was based on knowing their number of home runs hit. So based on their number of home runs. So that last part, this part B, was kind of like a recap or a little review from the topic 1 notes. Okay, your turn. So go ahead, you can pause the video and try this part A and B on your own. Remember, we're using the same equation from the front, so I'll rewrite it. Y hat equals 1.25x plus 550. Remember, where x is your number of home runs and y hat is the predicted number of runs. Go ahead, try this now for the Padres and both parts A and B, and then see how you did. Okay, go ahead and check your answers. Hopefully you plugged in 154 for X in part A, and you got about 742.5 runs. Show your work. If you want to round that accordingly to 743, that's fine. And then for part B, to find your residual, remember it's actual minus predicted. So we have a negative residual here, negative 105.5. You're welcome to keep it as a decimal. As you can see, that's what I did here. The 2008 Padres scored 105.5 fewer, because the residual is negative, runs than predicted based on their number of home runs hit that season. Okay, now we're going to go into interpreting. So our least squares regression line has 2 parts. It has slope, it has a y-intercept. So remember, statistics, it's all about bringing out the meaning in this data. So it's important. So we have this number that's the slope. We have this number that's the y-intercept. But what does it mean? So it's important that we understand what these actually mean in context. So the slope. Here's some general interpretations, you guys, to help you with slope and y-intercept. So if you want to, I'd highlight this maybe on your notes. Okay, so let's see here, the slope. Remember, you guys, from algebra, slope is the predicted change in the y variable for each increase in the x variable. So here's a general interpretation that you can kind of follow to help guide you through your interpretations for slope. Now, so remember, so if we want to, you can highlight, remember, it's the change in y that's associated with each change in 1 for the x variable, 1 increase in the x variable. So the y-intercept, remember back from algebra, the y-intercept is our predicted value for y when x is 0, okay? So when x is 0. A little cautious with the meaning for the y-intercept, you guys. A lot of times we don't have data around x equals 0, so we really have to, they kind of, what's called, I'll explain in a minute, extrapolate the line to figure it out. So not necessarily is there meaning for the y-intercept each time. And I'll explain that a little bit further in a second. But yes, be careful, be cautious when the y-intercept certainly is negative, okay? Certainly be cautious when the y-intercept is negative. Here's a general interpretation that might help for you when interpreting the y-intercept. But ultimately, for the y-intercept, it's the predicted value for y when x is 0, okay? So remember back, here's our equation that we were using. X is the number of home runs. Y hat is the predicted number of runs. So it says, interpret the slope of the least squares regression line in context of this question. So remember, slope is y over x. So think of it as 1.25 divided by 1, because my slope is this number right here. It's the coefficient of x, so it's 1.25. So think it's y over x. So if you're looking up here kind of at this general template, it's for each increase in the x variable. Well, what's my x variable here? Your x variable is home runs. So for each additional home run, now the slope comes from our least squares regression line, which is used to make predictions. So in both the interpretation for slope and y-intercept, the word predicted needs to make its way into your interpretation. So for each additional home run, we predict the number of runs to increase. I'm going to use the word increase here because my slope is positive, by 1.25. Okay, again, make sure to have the word predict because slope comes from the least squares regression line, which is used to make predictions. So we have two questions here for letter B. First one is the y-intercept. So my y-intercept, interpret that value. Remember, the y-intercept is, it's your constant in your equation, so it's our 550. So it's when x is 0. So think of it as 0, the 0.0550. So when x is 0, well, what's x? X is the number of home runs hit by the team. So when a team has 0 home runs or when a team hits 0 home runs in a season, again, we need the word predict because it's used to make predictions. We predict the team will score 550 runs. Let's see here. So second question, does the y-intercept have meaning in context? Explain. Couple ways you can put it here, you guys. If you know baseball, you know that you can still score runs without hitting home runs. But then some of you who also know baseball know it's a lot harder to score runs without any home runs hit. So it's pretty much, a lot is based on your explanation here. So I'm going to go with yes, because a team can still score runs without hitting home runs. Certainly, like I said, be cautious when the y-intercept is negative. Okay, certainly if the y-intercept was negative 550, it wouldn't make sense because no matter how bad the team is at baseball, the fewest number of runs they could score would be 0. Okay, not negative. But like I said, a lot of times we don't have data around the y-intercept, so the y-intercept could maybe not necessarily have meaning in context. But this one, a lot is based on your explanation. And I assure you for the quiz on this chapter, there will be enough information in the problem or whatnot so you can make, you can understand what's going on with the y-intercept. and make the decision you need to make on whether or not it has meaning in context. Okay, last term for today, extrapolation. Extrapolation is when we try to predict the value for the response variable. Remember, your response variable is like your y variable, for a value of the explanatory variable that is much smaller or much larger than the other values of the x variable, your explanatory variable, in the data set. It is risky making predictions using extrapolation since the association between the variables may not stay the same outside this pattern of data. So let me give you an example. Let's say I take information on people in this class using height to help predict weight. So let's say the smallest person in this class, the shortest person in this class is 5 feet tall, 60 inches. And the tallest person in the class is 6 feet tall, 72 inches. So this is height. This is weight. You don't necessarily need to write this down, you guys. You can just try and understand it. So I take everyone's height and weight down, make a scatter plot. Okay, looks something like this. Now, let's say someone walks through the door that's 6'4", that's 76 inches tall. Using my model, can I make a prediction for that person's weight? Nope, because I only have information on people who are 60 to 72 inches tall. Same thing if someone were to, like maybe a younger child walks through the door that's only 4 feet tall, so 48 inches. Can I make a prediction on this end as well? Nope, because both of those values are smaller than larger than the rest of the X values in my data set. I only know the pattern from between 60 and 72 inches. I can't make predictions outside these values, outside 60 to 72 here, okay? And that's basically what I mean for this. And that's why a lot of the times the y-intercept could possibly not make sense in context, because the y-intercept is when x is 0, and a lot of times we don't have data around x being 0. Okay? Good luck on your topic 2 worksheet for tonight.